Dr. Gogineni is the Dean. Okay, I'll start. Dr. Gogineni is the Dean Akers Distinguished Professor in the Department of Electrical Engineering and Computer Science at the University of Kansas, with more than 2 decades of research and teaching experience in radar remote sensing of the Earth, including polar regions. Dr. Gogineni served as a director of the Radar Systems and Remote Sensing Laboratory at the University of Kansas before serving as manager of NASA's Polar Research Program 1997 through 1999. He's currently the director of the Center for Remote Sensing of Ice Sheets. He was given the NASA Terra Award in 1999, and in 2002 he received the Louis Bird Graduate Educator Award at the University of Kansas and conducted research at the University of Tasmania as a Fulbright Senior Scholar. I would like to also acknowledge that the NSF-sponsored Polar Environment IGERT program, who organized a reception and dinner later tonight. Thank you.
It's good. Thank you, Professor Hartoff, for the introduction. And I also would like to thank Mary Albert, who invited me, and Fern Pate, that took care of the logistics and other help needed to come here. Before I go on, I have a little bit of a story to tell. I actually have been spent about almost 30 years in polar research. When I was a graduate student working on polar research, I was preparing a set of radars to go to Arctic to do some experiments on sea ice. And we were calibrating the radars outside our laboratory. And there was a lady that was walking her dog. And she came by and asked us what we were doing. I was very excited about somebody took some interest in our work, so we explained to her that we are sending these radars to look at sea ice in Arctic. And she asked me, what is the use of that? And we told her that sea ice plays a major role in atmosphere, and it's also important to operational applications. She looked at the sky and asked me whether I can tell whether it's going to rain tomorrow or not. And I said, no, I can't. Then she actually very stomped her feet and said, what is the point of your research, and walked away. So don't do that to me. You can ask me questions, but I can't explain what is the use of my research. I do enjoy building radars, and I think using them to polar applications, and I think I'm going to share with you some of the excitement we have in building these radars and applying and showing some results where the future is going to be. Before I go ahead, I also want to acknowledge the work of my colleagues. This work, where it involves several sensors, is not possible without the help of them. And in fact, I was highlighted the young people that are in the early career stages in red, and the blue, all of the graduate students that contributed to the presentation material that I'm going to share with you today. And I also had a long-standing collaboration with a lot of these people, and it's difficult not to forget some people on this list when I've collaborated with so many people over the last 30 years, and I apologize to any of them that I missed. My outline of my talk is I'm going to introduce you to why we're doing this, and some of the challenges associated with application of the radar to the polar research. Really, what are the challenges? And talk about the instrumentation we developed, and show you some sample results, and discuss what I think would be the future for radar remote sensing research, particularly for the polar regions, and then conclude my talk. And many of you have seen that if you looked at the satellite observations, rapid changes are taking place both in Greenland and Antarctica. If you look at this, blue areas are losing heavily the mass. I think actually if you look at the whole Greenland ice sheet is losing mass, even though the center is slightly gaining mass, but the margins are losing heavily. And the margin loss is much higher than what is being gained in the middle. So there is a net loss of mass from the Greenland. And the same thing is happening at the West Antarctica. There's a significant loss of the mass. If you look at these charts, these are charts are produced by different people using mass budget analysis, gravity measurements, and satellite radar interferometry. If you look at these large error bars, but none of them are showing a growing trend. All of them are showing that the ice sheets are losing mass. So there is a net mass loss both in Greenland and Antarctica at this stage. And this has definitely impact on sea level rise. In the IPCC in 2007 report predicted the sea level will rise between 18 and about 60 centimeters. And in fact, they upped the lower bound and decreased the higher bound and the increase in the sea level in the next century. But they put the following caveat. You can definitely read this quicker than I can read it. But what they have done is none of the models that they've used to predict the sea level rise include the dynamic processes that are taking place around the ice sheet margins. So they are used on ice sheet models based on the shallow ice approximations. So they do not include these processes that are going on. And this has an impact on a lot of the populations. In fact, if you look at the US, all these places would be affected if you have 6 meters of sea level rise. And this would happen to parts of India. And in fact, this I generated it with the help of folks at Haskell Indian Nations University. My wife and son were going to India to visit a family one time, and my son asked me where we come from. I was trying to show the Google map, and I found out this area is only about 6 meters above the sea level. So this is really a rice basket and very heavily populated so that you can see the impact. You don't need 6 meters of sea level rise, even if you have 1 meters of sea level rise, and you impose storm surges and cyclones on top of that. That's a serious impact on the people. So that's the reason why we need a more accurate prediction of what is going to happen to the ice sheets and what that impact will be on the sea level rise. That sets you the context. Now, if we want to improve the ice sheet models to be able to do that prediction, we have to have a very good information on the ice thickness. And in fact, this was produced by my former colleague at NASA, and I quoted him because he says that clearly that we really need to have the bed topography, basal information on the basal conditions of these fast-flowing areas in Greenland and Antarctica if we want to improve the ice sheet models. And so that means we need the radar technology to be able to sound these areas. And we also can say the same thing about the sea ice. Doesn't have the impact on the sea level rise because sea ice is sitting on the ocean, but sea ice controls the ocean atmosphere and interactions. It is a thermal insulator, it controls that. And actually, sea ice thickness is the key information that's needed to improve that models that incorporate the sea ice. But thickness is one of the most difficult variables to measure for the sea ice. Right now, they're going to use the cryosat IceSat freeboard measurements, measuring how much is floating above the water. From that, you're going to estimate how thick is the sea ice. But snow thickness over the sea ice complicates that. Snow controls the interaction process. It also acts as a mechanical load, and it depresses the freeboard. And the freeboard estimates are in error if you don't have information about the snow thickness. So we need some way to measure that. Also, accurate thickness information is essential both for the operational scientific applications, and that's basically the reason why we're trying to develop these radars for sounding the glacial ice and sea ice. And the challenges are radar sounding of glaciers and ice sheets is extremely well established today. In fact, the early pioneering work was done by somebody just next door to you at the Krell Laboratory. Amory White did it in the 1950s. actually a lot of people had doubts, but he persisted even when he had some failures and did that. He is the pioneer that established the radar sounding of ice sheets work. I don't think he received the recognition he should have. And in fact, he is the first person that also did airborne measurements of the ice thickness in Antarctica. So there is a history in Hanover that deals with the ice sheets. And if you take the interior of the ice sheets, you can take an off-the-shelf commercial radar and use it. And here is a case where we are showing what we are measuring with our current radar systems on the aircraft. The green is the case where we obtain very good thickness data. This one line is basically we were testing a new concept. Ignore that. But if you look at that, red is where we can't obtain the good ice thickness data. And you can see that all of those areas are located around the margins of the ice sheet. And that is what the challenge is, to be able to sound these areas. Why is it? Because these areas are extremely rough, as shown here. So they introduce what is known as the clutter. And also, because these areas have a warm ice at the bed, they have very, very high loss. So those are the two reasons why sounding those areas is extremely difficult. And so here is an illustration of the surface clutter effect. If you go to the radars that have to be used to sound ice have to operate in the VHF and HF or UHF frequency range. This is a long wavelength. That means the size of the antenna that you can put on an aircraft is limited. You can't put a very large array. So that means you're going to have a very broad main beam as well as the large side lobes associated with that. In the interior ice, as you can see that most of the signal from the side lobes goes away. In the time-wise, this signal is appearing at the same time as the echo from the bed of the ice. So you can't separate them based on the time. So, but if the signal goes away from you, you can see the bottom of the ice very clearly, surface of the ice very clearly. By the time of the flight, you can estimate the ice thickness, knowing the refractive index. And that's what we do. And you can take any off-the-shelf COTS radar and you can do that in the interior very effectively. When you go to the margins, as you can see that this is what I've shown in the red, you can see that some of the signal is coming back towards your radar. This signal, even though it looks small, this is probably much stronger than this because you have to, the electromagnetic wave goes through a lot of attenuation in going from the surface to the bottom of the ice. So this is an extremely weak signal. So this signal is masked by the surface clutter. You can see that that's what we're showing here. Now, if I can do an advanced processing and get the signal from not come back, as you can see that I moved this side lobe to here so that I don't get any signal back, then you can see that I can actually clear up the clutter and get the bed echo. So you have to do that sort of advanced processing to get the bed echoes from difficult areas. In fact, this is from an area called Helheim Glacier. This is the first successful ice thickness measurement over Helheim Glacier. So those are the results that are shown here. So you can use the SAR processing to reduce that in the along track direction, and you have to do the array processing like I illustrated here to reduce that. One of the challenges you have to face when you're doing the array processing is wing flexure. That is, wings of the aircraft are not static, they move. When they move, the phase change between the elements degrades your beam formation. You have to sense and correct them, and you have to correct it to a precision of 2 to 3 degrees between the elements and less than 0.5 dB. That's a major challenge with the sparse array. And another thing is, you want to detect weak signals, you have to have a large power aperture product. That is what radar sensitivity is determined by. The radar equation tells you that if you want a sensitive radar, you have to have a large power aperture product. You can't keep on increasing power in an aircraft unless you are in a big military aircraft with the C-130s and others. So that means you have to use smarter techniques like a pulse compression, where you transmit a long pulse and compress it to a short pulse to obtain a high peak power that's required to detect these weak echoes. The artifact of the pulse compression is range side lobes. Range side lobes is when you compress it, it will have a sink response or sink square response. So that strong surface echo can mask the weak bed echoes. So you have to obtain extremely low range side lobes. And also, radio frequency interference is a major problem. For all of us, computer and PDAs and all of those are a boon to us. For a highly sensitive radar, they are a problem. If you take a computer that you have, you are allowed to radiate 150 microvolts per meter, 3 meters away from that. But the radars that to sound some of these areas have to measure signals as low as 3 to 5 nanovolts. That means that is 80 dB below what you are allowed to emit. So that means you have to do something about the RFI. So we have to do all of these things to control this. This is the wing flexure. As you can see that this is what I'm illustrating here. There's antennas 1, 2, 3, 4, 5 on each wing of a twin otter. What we did was we took the phase difference between this element to this element to this element and plotted it. This is between the elements 1 and 2 here. As you can see that it's not much variation because it's a little bit more rigid there. As you go to the 1 to 5, you can see this phase is varying almost 10, 15 degrees. So that you have to sense it and correct to a precision of 1 to 3 degrees. And the accelerometers are not good enough to do that. You have to use radar data itself to correct for this. And here is the effect of the actual wing flexure. You can see that the beam, we are just moving the beam from this to here and back here. You can see that the beam moves as you do that. So all of these have to be sensed and corrected in real time. Here is the radio frequency interference. This is what you get if I terminate my receiver in the 50 ohms. That is the noise generated by the receiver. If I just open up my receiver, you can see this is the noise you get because of the emissions from spurious emissions from the computers or other subsystems. You have to control all of this. To get that, not only you have to control in the hardware, and you have to do something in the signal processing. We have done that. Here is the blue case where you got the RFI, and by doing the advanced signal processing, we reduced that by 20 dB to reduce the RFI impact to deal with that issue. Here is the range side lobe issue. This is the case where we actually take a signal, taper the amplitude, and weight it with a different weighting function like you do in a DSP when you take a Fourier transform. And blue is the case after we correct for the system effects and the impulse response of a point target. You can see that we obtained almost close to 80 dB side lobes. This is really a weak target that is present there. That's why you see this here after we do the process. So we were able to obtain a range side lobes of almost 70 to 80 dB with our current system. Using all these improvements, we developed this instrumentation package. This is called Multi-Channel Coherent Radar Depth Sounder and Imager. That's what that acronym is. It operates at 195 megahertz with 30 megahertz bandwidth. We also have a capability to operate it with 80 megahertz bandwidth if necessary. And it has been operated on DC-8, P-3, and twin otter aircraft so far. And here is something called a KU band altimeter. It is operated with at a center frequency of 15 gigahertz with 5 gigahertz bandwidth. Now we expanded it to 6 gigahertz bandwidth this year. This is used to measure the surface elevation, near surface internal layers in polar firn, and also the snow, ice, snow air interfaces. Here is what is known as the snow radar. This is operates at a center frequency of 4 with a bandwidth of 5 gigahertz. And it's been operated on the DC-8 and P-3 successfully. And we also have a radar called Accumulation Radar that measures the internal layers and ice thickness. And this is operated on both P-3 and twin otter. One of the things that I want you to notice is this is operated from an altitude of almost 500 to 1,000 meters. It only transmits about 200 milliwatts of power. And actually it doesn't even interfere with the radar altimeter on board. And it's all of the performance is obtained through the signal processing. And the two in the reds are the ones that we are developing. We are developing a radar that operates at 14 and 35 to look at temperate ice and also supplement what we are doing with the high frequency sensors over the margins of the ice sheets. And we are also planning to develop a radar that operates between 75 and 300 megahertz to sound sea ice in the future. here is the antenna array that is used to make measurements on the Greenland and Antarctica from the P-3 aircraft. This is a 15-element array. It's not completely filled array because you can't put antenna elements wherever you like on the aircraft surfaces. We took where we can put them and deal with them in the signal processing. There's 7 elements here, 4 elements here, and 4 elements here. So the total 50. This is the largest array to be flown on the NASA P-3 aircraft for any civilian applications. I'm not aware of any classified, but to the best of my knowledge, this is the largest array that has been flown. And here is in the flight. This has been flying for 2 seasons successfully, and it's going to go again to Greenland in March and April. And here is an array on the DC-8. This has got a 5-element array. The DC-8 measurements are made with the aircraft taking off from Punta Arenas, going to Antarctica, making the measurements and returning there. So it's a 12 to 13-hour flight, and you only get 4 hours on the target because of the transit takes almost 8 hours. And what they gave us was they said you can't reduce the aircraft range by more than 2.5% if the radar has to be on board the aircraft. And that's why we had to restrict it to 5 elements, and we restricted the range by 1.75%. So we met the spec and exceeded it. And here are, so those are the sensors. And I'm going to show some results. This is a glacier called Jakobshavn in Greenland. It drains almost about 7.5% of the ice in Greenland. It is used to be the fastest flowing glacier on the surface of the Earth. And here is the 3 cuts across the glacier. And here is the echo. This is the surface of the ice. This is the bed echo. I think you can see the very, very big, weak bottom echo here. This ice is about 2.5 kilometers deep at that point in the channel. And here again, you can see the 3 cuts. And what I'm trying to show here is the following with this, and this is, you can see that we get definitely discernible echo, but only 2 to 3 dB above the thermal noise of the receiver. And here, what I'm trying to illustrate is I took an amplitude response at this point, a scope called, and here also an amplitude response at this point. If you look at this blue is the response here, and this one is the response here. The difference between this and this is about 70 dB. The ice is basically about 1.5 kilometers. So you are experiencing 70 dB of loss for that 1.5 kilometers ice. Contrast it with what you're going in the middle of the ice sheet is probably about 60 dB loss for 3 to 4 kilometers of ice. So that is why it is a challenge to sound these areas, and we have done that successfully. And here is a case, some more cases I show that we have a clear bed echoes, and this is how the surface looks like. You can't make surface-based measurements there. And so you can see that, again, the cuts. And here is the case where another cut across it, and as we're going along the glacier, these are the data that we obtained. As you can see that, I took these portions, zoomed in, and showed that the reason I was showing that is you see 2 clear echoes, one from here, one here. We think these echoes are from the temperate ice at the bed. We think there is anywhere between 200 to 500 meters of very wet ice at the bottom. That's the reason why you're seeing the extremely high losses, and also why that glacier is moving very fast. And here is again, you can see that the 2 echoes near the calving front. This is the upstream. So this is to illustrate that we really have very discernible echoes, and that's what we use to generate the bed map. So using that, we generated the bed map for the Jakobshavn Glacier. This is available on our website, and people can use that, and the modelers are already using that. And this is for the Neem site. We used interferometric techniques and others to do a 3D topography with fine resolution. And this is for the Helheim Glacier. This is for the Russell Glacier. So we are making significant progress to address those challenges, get the data that are needed to improve the models. And we've also developed, because we have a cross-track array, we do radar processing similar to the tomographic processing in the medical field with the radar. So take slices and do the cross-sectional processing so that we can produce 50 meter by 50 meter footprint normal cases, it will be 50 meters in the along track. Without the tomographic processing, it will be 300 to a kilometer in the cross-track direction. You can't really tell where the signals are coming from. This is the tomographic processing that resulted in this. And in fact, grip core was drilled here because they didn't have access to this sort of processing and data when they selected the drill site. And I think this drill site was selected next to a relic river, and that's why the bottom of the ice is disturbed. And so you need this sort of processing if you want to select optimum ice cores. And here is the case. You can see that the internal layers are significantly disturbed. Because of the cross-track array, we can estimate what the direction of arrival of the signal is and determine where the nadir signals are coming from. As you can see, blue is the case where the signals are from nadir, and other colors are the signals are coming from either side of the radar track. So you ought to be able to do that in the future to select optimum core sites. And we have also done it for the Neem. Neem is the new drill site, and we have done this from the airborne data to produce this high-resolution data to determine the bed topography with very fine resolution to select the cores in the future. And again, you can see the disturbances at the bottom with this new technology that you can identify early before you select the sites. So what we recommend is, if we're selecting an ice core site, you do an airborne site to select, airborne survey to select the site to within 500 meters or 500 meters using the new technology, and then do a surface measurements over a 10 kilometer by 10 kilometer grid to select an optimum drill site within 25 meters by 25 meters. That doesn't guarantee that you're going to drill straight to that, but the site would be optimum based on the radar data. And the technological improvements we made also resulted in a new finding recently, that we found the deepest subglacial trench in Antarctica. And it is known as the Bentley Trench until now, that is about 2.5 kilometers below the sea level. This one is about 2.7 kilometers below the sea level. And I think there is one more that is 200 meters below that. So the deepest trench is located in East Antarctica, not in West Antarctica. And another thing that I wanted to show was these are the data that was collected here on the ice shelf. This is the surface of the ice shelf. This is the bottom of the ice shelf. And if you see the backscatter here, that means with this, what is known as the accumulation radar in the future, we would be able to do INSAR and tomographic processing to be able to estimate the bottom melt rates of the ice shelves. That's a significant development to transform the science of how ice sheets melt and the impact on their disintegration. But with all of these improvements, there's a price to be made. Even with the 8-channel system, we collect about 2 to 3 terabytes of data for flight. In some cases, they're flying almost about 30, 40 missions each field season. And so we're ending up with huge amount of data. Right now, we set up so that we actually can do on-site processing using the computer technology we have to produce results within 24 hours so the scientists can see and say there is something interesting, we need to refly or we need to do some analysis of this. And that can be done 24 to 48 hours. And the results are posted on this site within 24 to 48 hours after a flight, even with that volume of data. We have close to about 800 terabytes of data from 3 field seasons in Greenland and Antarctica right now in our computing facility. All of the improvements we made have also resulted in technology that can be used to sound glaciers from very high altitude. These are data collected from with the DC-8, a jet aircraft flying at about almost 450 knots at about 80 to 50 meters above the surface. This is the ice surface. This is the bed of the thing, and these are the internal layers. And this thickness of the ice is about 3.2 kilometers in this area. This was sounded. This is the first time anyone has sounded ice from a jet aircraft flying at jet speeds over the ice sheets. We were able to do that because of the advanced signal processing and technology. And again, Here is a case I just show that without, this is the raw data or SAR processed data. Unless you do the advanced MVDR or array processing, you cannot see the bed echo, which I'm just highlighting with the laser pointer there. Here is the case again. When you do just the SAR processing, again, Clutter is masking the bed echo. Once actually you do the array processing, you can see the bed echo here. And it's the same case here. This is from a low altitude. This is from high altitude data. Here you can see that before we did the array processing, you can't see that. Once we do the array processing, you can see that very clearly. The bed echoes at the same range as what you collected from high altitude. What is the advantage of doing high altitude? You can cover more area faster and also longer range because the fuel consumption is low. And again, the same case, here is the low altitude. Here is the high altitude data. I can see that it's 65 microseconds, which means close to 9,000 meters at 10,000 meters above the surface. You can't see the bed echoes. Once we do the advanced processing, you can see that array and SAR processing. So the work we are doing for the fast-flowing glaciers is also contributing to be able to do this more effectively from high altitudes in the future. And these are the data we collected from high altitudes. Green means good data. Only areas we didn't get good data are these areas in Antarctica. And these are the Greenland from high altitude. And the second one I wanted to illustrate was the accumulation radar. We developed this radar so that to map the internal layers in the polar foam and basically date them and track them to estimate the annual accumulation rate. And that's why we call it accumulation radar. And this is over the Greenland ice sheets. This is basically range side lobes associated with that. This is the surface of the ice. And these are internal layers almost going to a depth of about 200 meters into the ice. And so you can see the layers clearly all the way from the surface to about almost 200 meters with that radar. And one of the things we found was that radar also is able to penetrate low loss ice, and we can sound the low loss ice in the Canadian glaciers. So this is the bottom of the ice. As you can see that we're getting a pretty good bottom echo of 500 meters. And the processing here is wrong because we normally process the accumulation radar data with the dielectric constant of 2 because the foam is not densified fully. And whereas ice, it's about 3.15 or 17. So this is processed with 2 since the same algorithm was used here. So you have to scale that. And another thing that we saw with that radar was we flew over a glacier called Peterman, which you probably heard in the news that there was, it broke off and there was a lot of coverage about that. This is over the Peterman Glacier. This is where the calving front is. This is the bottom of the ice, and this is the multiple of the ice. Normal radars do not reveal this structure. If you look at the bottom, shows as one thick line. But if you look at this, you can see that there is platelets or ice blocks sitting on each other. So the bottom of the ice is much more complex than known until now. And we have come to know because of this high-frequency, wide bandwidth systems that we are using today. I don't know what the implications are to model those in the future, but this is the structure you have at the bottom. And this is what the snow radar results are. As you can see that in the top 20 meters, we get very fine resolution internal layers so that you can date them and get the accumulation for this. This is over a Pine Island area. This is the snow radar, and KU band altimeter also penetrates through quite a bit. One of the interesting factors you have is if you look at the surface is not the strongest return. This one below is the strongest return. That means that has implications on how you interpret cryosat data. And the radar, again, you can see that this is trying to measure the snow thickness over sea ice. This is no snow. You can see that there's only one echo. Once you have the snow there, you can see the snow-air interface as well as the snow-ice interfaces to be able to estimate that. That is in the snow radar. KU band operates at a higher frequency. You can't see that because it's not penetrating the snow in that area. Here is more examples of that. Again, snow air, snow ice, snow ice, snow air. These are data collected with the radars on the aircraft flying at an altitude of 500 meters in the Weddell Sea area. And again, another example of what we're getting with those radars, same radars over the ice sheets, both internal layer, both at the snow radar and KU band frequencies. Some more results for the in fact, CryoVex is the cryosat validation experiment. And here are the point targets they put on the ice so that you can geolocate them. And here is basically the snow-air interface and snow-ice interface clearly seen with this radar for that validation, both in the KU band and snow radars. Same thing again at the Weddell Sea in the 11. I'm just thumping through some results to show you that. One key thing that we wanted to show was, if you look at this here, what we did was we wanted to see what cryosat is going to estimate in the snow-covered areas over sea ice. The red is basically what we see with the high-resolution radar. Blue is what cryosat waveform will look like and what it's going to measure once we degrade the resolution. Let's consider that you're doing a peak tracking for the cryosat. And if you look at this point where there is no, see that this is the point here. When there is no snow, both of them see the same thing. Okay, go to here where there is a snow here. You can see that there is a snow-air interface, snow-ice interface are being seen. But if you measured with the cryosat, you're seeing something there. You're not seeing the effect of the snow there. But you go here, you see again you're measuring something in between. Here is the snow air, this is the snow ice, but you're measuring something here. So it's same thing here also. You see that the cryosat data are going to have 60% of the cryosat data where there is a snow are going to be affected by snow cover. So that has to be factored in when you're trying to do the freeboard conversion into snow ice thickness estimates. And we also, because we have a multi-frequency sensor package, we were able to detect something that was not known to be happening in Greenland. What we found was there is a surface melt during the summer, the water percolates and the lake is formed. The lake survives the whole winter under the snow. This is extensive. Here is basically the surface of the snow, and here is the interface of the lake. So we found extensive lakes on the surface buried below the polar fern that survived the whole winter during both in the east coast, west coast, and northeast also. And if you look at that, it is not shown in the KU band. You can't see that in the depth sounder because it doesn't have the resolution to see that. You can see that in the accumulation radar. So the only two radars that can see that is that. So having this multi-sensor package is what allowed us to see this. And another point I wanted to illustrate was the snow radar. You can actually also look at the crevasses. So this has operational applications. And if you look at this is the KU band. It's not penetrating to see that. And if you look at the snow radar, you can see these. These are upstream. As you move downstream, you can see very clearly these crevasses and buried with snow bridges with this radar because of the bandwidth. And here is another data set where you really can see very clearly the snow air, snow ice interfaces with these radars. Okay. And I'm just going to skip that. That is what we're planning to do with the temperate ice sounder. All I'm showing here is we actually did a surface-based experiment to show that we can use that at those frequencies to sound ice, both in Antarctica and Greenland. In my view, that tells you what are the challenges, what we accomplished so far, where we are, and this is where I'm going to project what we'll be able to do in the future. I think we can develop a radar that operates from 140 or 150 megahertz to all the way 600 megahertz to put on an aircraft, so that you can actually map the whole ice from the surface to the bed with 50 to 60 centimeter resolution. So that is the resolution you will be able to map the internal layers in the future. And we will be mapping the internal layers with very, very fine resolution, just like I've shown, to continue that. And I think that we will have a sensor to be able to measure the bottom melt rate of ice shelves. Right now, people go and do that by drilling a core at some point to estimate that bottom melt rates. You can only do in few places. If you want to do it in an extensive way, you have to do it with the radar on an airborne system. And I think we can do that. We also, by having a wide bandwidth, you can actually estimate what is happening at the bed very unambiguously. See, the reason is, if you have frozen bed to wet bed, the backscatter difference or reflectivity difference is about 12 dB. That 12 dB could be wiped out very fast because of the roughness effects. If you have a single measurement, you have an amplitude and phase at the most, and you have two unknowns, or maybe three unknowns, because you also have to know the loss through the ice, and you have a under constraint system of equations to invert it. But if I take the same thing at a chunk of frequencies, then the same parameters I estimated have to be explained at the other frequencies. So then I have an over-constrained system of equations to be able to invert that unambiguously. And that's what this wide bandwidth system can do. And I also think that we can extend the frequency range of the SNO and KU band so that it's one system that covers all the way from 2 to 18 gigahertz, so that you can map the layers with 1 to 5 centimeter range resolution in the future. And I also think that sounding of sea ice is possible. We have done simulations. Because of the time factor, I have not included them, to see what sort of optimum sensor can be used to measure the sea ice thickness. And we came up that the sensor that needs to be is between 50 to 300 megahertz, and to measure sea ice between 1 and 15 meters thick. And we would be able to develop that with the current technology, that sort of a sensor to be flown on that. Based on this, this is what I project to be the radar to be operated 140 to 600 megahertz, 2 to 18 gigahertz to do all these measurements. And the sea ice, this can do also all of this on the sea ice. This is in the glacial ice, and a temperate ice sounder, as well as the sea ice sounder that operates over that frequency range to do that. And we actually, these are not waving hands to some extent. We have done simulations to verify we can develop that sort of an antenna array. Here is basically a 36 element antenna array we have simulated using a EM simulator, and verified its antenna pattern, gain, and return loss. And we have also demonstrated that using the current system, we can generate a nadir beam, left beam, and right beam with enough isolation. If you look at this, the left-right, there's more than 20 dB isolation. Couple this with a technique like a CDMA. You have each beam has its orthogonal chord, then you can get 20 dB more isolation. So that means the left-right will be 40 dB isolation, and you shape the beam, then you can image anywhere between 5 to 9 kilometers of swath in one pass. So that's going to be a major technical advance to be able to generate fine resolution bed topography to support glacial ice sheet modeling, glacial hydrology work, ice core studies in the future. So this is basically shows you that this is possible, and this is possible because we are able to do the advances in antennas driven by defense and communication industry that taking advantage of that. And here is the case. We actually improved that snow radar. As you can see that right now, this is Hanning window, which is 32 dB side lobes. That is the 32 dB side lobes for a point target. We have achieved that with that radar in the future. And we think that we can do this with 50 to 60 dB side lobes, which means we can extend the range of snow thickness we can measure from almost 5 centimeters to 2 meters. And this sensor will have applications in snow avalanche studies and other applications beyond sea ice and others. And also, we are developing more accurate signal processing techniques, and I think there has to be research in there to do that, so that you can form nulls to get rid of the clutter and in the presence of wing flexure and other things. That's a thing that has to be done in the future. And here is basically what we think we can do, and this is the case where I show that you can simulate multiple phase centers to be able to do tomographic processing or INSAR processing in the future. So that is what we want to do with the Basler aircraft if we get adequate resources and funding. But there are a lot of challenges. You know, when we use the 16 or 32 channels sampled at 1.5 gigahertz rate, you're going to end up with 54 terabytes of data per channel. Okay? So that means you have to do onboard data processing to reduce it to 0.5 terabytes per channel. And I don't see these challenges as insurmountable. I see this as an opportunity for PhD dissertations and master's theses. So that's what my summary is. There's a lot of engineering students. Yes, there are technical challenges in pushing this technology to do transformative science. And that can have very nice technical and scientific dissertation to be able to address them and collect data and use them. So in summary, we design and develop radars that really are addressing the scientific challenges associated with sounding and imaging the fast-flowing glaciers. We have generated data products that are currently being used in the models and contributing the advanced instrumentation, and others are contributing to wider polar research. What we did for ice sheets have contributed to sea ice already. So that's what I mean. And I really believe there is an opportunity to develop radars that can transform polar science, and I'm willing to say if we do that, the next decade is going to be the decade of radioglaciology. And so that's what I wanted to end. And I also wanted to say one thing, that you can read this, and Henry Ford said that basically, I'm just going to read this: I invented nothing new, I simply assembled into a car the discovery of other men behind whom were centuries of work. I believe that it's the same thing with what we were able to do. We were able to take advantage of the advances in the computing, advances in the digital technology, DSP, and A to D converters and D to A converters, RF systems and antennas, to be able to put together systems what we can do today. And I do believe in what he said, that it's comparatively responsive for the greatest forward steps, and it's utter kind of nonsense. I think it's a teamwork, and I do hope that teamwork will prevail in the future too. And I think there is the time is right to really put in the investments to advance this technology so that the glaciology and polar research can be transformed. Thank you.
Any questions from the audience?
Yeah.
You showed some photos of the extreme ice. Excuse me, I forgot what I was going to say.
Outlet glaciers.
The surface roughness, the extreme surface roughness, especially at the margin,
Yeah.
where there's not an ability to have surface measurements. But have you been able to coordinate some of your measurements more inland with more contemporary ice cores or ground-based radar?
Yeah, actually, the upstream of the Jakob-Saven, when we did the Jakob-Saven survey, we did it over a 200 kilometer by 200 kilometer grid. And the upstream, where it's safe, they also performed seismic measurements at the same time we were doing radar measurements. Very fine. And also, some of the radar passes do cover core sites, so there is a validation of the inverter data at those core sites.
Do you have a sense of what is more cost-effective, airborne radars like yours and like Ice Bridge versus putting an entire satellite into orbit? Is one, obviously the aircraft are more flexible and can go to specific places, but is one a better deal than the other?
See, one of the things is they always quote Mars as a successful sounding of all of these things. But Mars, nobody can verify what they're actually looking at. Whether they're seeing in the very cold ice, I have no doubt they're seeing some internal structure on the bottom. In other places, and in fact, one time when I showed you the Accumulation results, my graduate student came to me very excited because he's seeing a nice bottom echo. And I was excited too, that this is such a nice clear echo that we did such a wonderful thing with the radar. And then I started looking at the GPS coordinate. The GPS coordinates indicated those data are past the edge of the ice. What it is when the radar was flying, it was tracking the color reflector of the edge, and it looks like it's nice bottom echo. So we were seeing that. So in terms of putting a satellite radar, the color issue really hasn't been addressed. There was a lot of hand waving. And even the data I showed you here, they were collected from a 3-kilometer ice from 8,000 meters above the surface. That means your color angle is at 45 degrees. So you're still getting quite a bit of spatial filtering with the antennas. When you put something in the satellite, you are going to observe the bottom at an angle of about 3 to 5 degrees. You're not going to have much of a spatial filtering with your antenna at all. So you have to reduce the color by almost 40 to 50 dB. Nobody has shown they can do that, but they're formulating satellite mission ideas without addressing that fundamental concept and hand-waving it.
Yes, are you, or have you attempted to filter the wing flexure effects in real time?
No, that's one of the things that we would like to do in the future. And basically what happened is we put accelerometers to do that. And the accelerometers are generating RFI noise to the cable that was there. So we had to disable the cables because it's a trade-off between few dB improvement or 20 dB loss. So we just disabled that. So unless we address that problem of well-shielded cables and careful design of the accelerometers, we can't incorporate that. But that's one of the young ladies actually is working on PhD dissertation on the topic. How do you sense and feedback onto the See, in fact, one of the things I didn't mention was the beam formation we showed you. Each element is fed with its own waveform generator and amplifier. And each one has an amplitude and phase correction. So we match them so that we can synthesize this transmitted beam with low side lobes. And those were measured transmit patterns in flight. And but we still need to push the side lobes to 60 dB, combined side lobes 60 dB or lower to be able to sound these areas. And that is an important thing to do.
I invite you to speak with Dr.